I'd like to welcome everybody. Good morning to everyone. Good afternoon, good evening, depending on where you're attending from. My name is Ernesto. I'm a research group leader here at the International Iberian Nanotechnology Laboratory in Braga, Portugal. And I want to welcome everybody who is attending online this event. And this is our first Quantum Portugal Initiative lecture. These lectures are a series of live webinars that we're organizing at INL to track research and development in quantum science and technology. So this field studies how quantum mechanics enables new ways of designing new materials, processing, communicating information, and developing new sensors. We're starting today and plan to have lectures every 2 weeks on Tuesdays. So please stay tuned to catch the talks announcements. So it is my pleasure to introduce our first QPI lecturer, Professor Pascale Senellart. She is a senior CNRS research director in France and a professor at Université of Paris-Saclay. Her research focuses on the generation and manipulation of quantum light for applications in quantum communication and computation. Pascale has received many prizes and recognitions for her research work, such as the CNRS Silver Medal in 2014. And in 2018, she was elected a fellow of the Optical Society in the United States. In 2017, she co-founded Quandela. It's a spin-off company specialized in single photon sources for quantum technologies. So Professor Sennelart has this dual experience, right, in academia and in a startup company in quantum technologies. So it'll be very interesting to see how she views this whole field. I see we have many attendees already. Which is good. Sorry again to everybody who is joining us now. We were a bit late because of technical problems, but I think everything's working now. If you have questions, okay, if you're attending and you have some questions, please post the questions in the Zoom chat channel. And at the end of Pascale's talk, I'll choose a few to ask her for the discussion after the presentation, okay? So without further ado, let me invite Professor Senellart to this virtual stage to give her talk. And the title of the talk is Quantum Light Sources for Quantum Technologies. Welcome, Pascale. Thanks again for accepting our invitation. You may share your screen if you're ready.
Thank you very much, Ernesto, for this kind introduction. I'm very happy to be here with you today and very honored to inaugurate your lecture series of the Portugal Quantum Initiative. I think it's a great thing that Portugal has launched this quantum initiative. You may know that we have the similar initiative launched in France very recently, and I think it's nice because this will give us opportunities to create links between our countries. So like Ernesto started to introduce, I should correct one thing because I need to correct it. I'm not professor at Université Paris-Saclay, I'm associate professor at École Polytechnique. So I just need to be clear about that.
Sorry, yeah, okay.
That's okay, that's completely okay. I'm working at the Center for Nanoscience and Nanotechnology. Here you see the pictures of our brand new building. We moved into this new building about 2 years ago. And in my group, we are specialized in the development of semiconductor devices for quantum applications in basically optical quantum technologies. So we basically give you a glimpse of what we do. We fabricate semiconductor chips that looks very much like regular electronic chips. If you zoom in, you would see these kind of wheel-shaped structures, which are actually optical microcavities. And in the center of this optical microcavity, we have an artificial atom, a semiconductor quantum dot, that emit photons one by one. So I will start with an introduction about motivation. Why do we need light in quantum technologies? What is the place of quantum light in all this broad field? So I would say that there are lots of possibilities offered by quantum light. Light has many flavors in quantum technologies. We can think of light as individual particles of light, photons, and this is a field where we encode the information in single photons. We call that discrete variables. But we can also consider light as a wave and play with this wave packet and play with the Wigner function of the state and encode light using a continuous variable scheme. We have also many degrees of freedom to encode the information when we play with light, which is also a nice feature. We can use path, having the photon going right or left, polarization, orbital angular momentum, time, energy, even photon number. So all this brings a lot of possibilities, and light, of course, is considered for many applications. The most emblematic one maybe would be quantum communications. Like in classical technologies, we can connect two places with light. The first application is quantum key distribution, although for quantum key distribution, it's been shown that we may not need quantum light to do that. We can use maybe attenuated lasers, so these are classical light sources, but with decoy state. But if we want to go to long distances or to go to high red QKDs, we may need efficient single photon sources. There is an area of quantum communication where we know that we will need single photons, is the area of quantum networks. If you want to connect different places at the quantum level, sharing entanglement, then we will build quantum networks with different architectures. I sketched here two of them. So architectures based on quantum memories, where we would link different links with photons, and in each node we would have a quantum memory, or other based on measurement. This is an approach where you generate light states which are more complicated, not single photons only, but many photons. Here you have, for instance, 12 photons. Each circle is a photon, and each line is an entanglement link. Another very important application of light is in the field of quantum computing. Single photons have been explored to implement quantum computing very early, actually, in the field. And there is good reason for that. The first reason is that in quantum computing, we don't want to have perturbation from the environment, and which we call decoherence. And actually, photons are non-interacting particles. They have no mass, no charge. So in vacuums, they interact with nothing. So in principle, it could be the ideal qubit because it should be intrinsically resistant to decoherence. Also, if you think of discrete variable, it's very easy to make single qubit gates. What does it mean? If I want to encode the information on polarization, I want to be able to make superposition on H and V polarization. Well, it's very obvious. You just use a wave plate in optics and you can do that. Optical quantum computing can be done at room temperature. It can be done on chip. And it's a natural path to what in the future we would like to do is to connect different quantum computers. And to connect different quantum computers, you will need light. And of course, if you're already using light to encode the information, that would be quite obvious to implement. Of course, all this would be too good to be true if there was not a big challenge that comes with it. And the big challenge is that photons interact with nothing. So how do you make photon-photon gates? And I will come back to that later. Still, single photons have created, no, not single photons, sorry. Quantum light has created a lot of momentum in terms of quantum computing. I did say I corrected myself because it's not only single photons, it's also the other approaches based on continuous variable. With the appearance of various startups, like PsiQuantum in the US or Xanadu in Canada, these two big companies have raised hundreds of millions of dollars already. In Europe, we work with smaller, different kind of investment, venture capital. So there was a creation of QX in 2019 and Orca in 2020 in Netherlands and in the UK. And I should say that the companies that we have created, and I have not planned to discuss it, but I can discuss it afterwards, is also working on the development of this optical quantum computer. And all this momentum has been reinforced very recently in December last year with the demonstration of quantum computational advantage, the other word to say quantum supremacy, if you want to be more specific about what you mean, with photons by this group of Zhanwei Pan in China, using something that is in between discrete and continuous variable, actually, which is quite nice. So what are the challenges to develop this optical quantum technology? And the challenge I'm addressing today, and actually we are trying to address in my group, is a challenge of quantum light generation and later on quantum light manipulation. So the ideal single photon source that we want to develop should produce light pulses, and in each pulse we should exactly have one photon, no more, no less. This is what we call an undeterministic, on-demand, so it's clocked. Deterministic, there is always one photon, a single photon source. So it's a dream to do that. In practice, we will always have losses, and when you have losses and you have only one photon, you end up with nothing. So the good metric to measure the efficiency of a source, which in the light source could be called brightness, is the probability to have one photon per pulse. So that's the first figure of merit. And then we don't want to have more than one photon. So this is a property that we call the single photon purity, and it's easy to test experimentally. You take your light beam, you send it on the beam splitter, and at the output, you have two detectors. If you have a single photon, you will never have two clicks at the same time. You just have one click. And this is how to quantify the single photon purity of the source. For many applications, we need indistinguishable photons. And I will come back to that later. What does it mean at the quantum level? But just for now, what we want is to be able to use this fundamental effect that is called quantum interference of indistinguishable particles. It's a situation that we learn in quantum physics, where you have two indistinguishable particles coming at the input of both input of a beam splitter. You have in principle four possibilities: exit together on up, right, or separately here. But when the particles are completely indistinguishable, you see that there is a plus and minus sign here, which makes these two possibilities to cancel out, and you end up with the photon exiting together the beam splitter, either by either one of the ports. And this is what we call the quantum interference of indistinguishable particle. And it's a way to implement photon-photon gates. If you have two photons that are indistinguishable, they will behave like this, if not, not. And then you can play with detectors and implement what we call linear gates. So how do we check that we have indistinguishable photons? Easy. Same situation as before. Instead of sending just one photon, I send two at each input of the beam splitter. And if they are fully in the same quantum state, they will exit the beam splitter together. So I will have a click here or there, but never to click at the same time. So it's also a way to measure indistinguishability. So there are two main types of sources to generate single photons. And the first one, based on frequency coercion, is the one that has been used in the last 15 years to push the field forward very efficiently. And I will describe this technology and discuss the advantage and limitation, and then focus on what we are working on, which is another technology based on single emitters. So you can obtain something that is very close to a single photon state by starting with a laser that you send a nonlinear crystal. And this nonlinear crystal, here I'm thinking of a crystal that shows nonlinearity of type Chi2 that generates photon pairs. So we will do that, but we pump the crystal very moderate power so that we hardly ever create a photon pair. So the state that you create when you do that is something like this. You have most of the time nothing. Sometimes one photon pair, so one signal, one photon in the idler, and sometimes two photon pairs. So in terms of efficiency of the source itself, you see that the probability of obtaining one pair is eta squared here. So this is not a single photon source, it's a source of a pair of photons, but the photons are appearing at the same time. So to obtain a single photon source, it's easy to just put a detector on one side here on the output path. And when you detect a photon here, somehow you project these states which used to have a very large fraction of vacuum to a state where there is no vacuum anymore. And you end up on the other side here on a state which is very close to a single photon state. Unfortunately, there is a little bit of two photon state as well. So it's a very nice way to obtain an approximation of a single photon source. But the problem is that if now we think of the single photon purity, basically it's coming from this probability of having two photons here. It's also scales at eta squared. So to have a good source, I need to work at eta as close as possible to zero, which means also the efficiency to get the pair in the first place as close to zero as possible. So these sources have still shown great advantages. They operate at room temperature. They can be used in multiple ways. You can encode information in multi-modes and stuff like that. There is an intrinsic limitation that the brightness, the efficiency of your source is equal to the error rate. So it seems like a big problem. Actually, there are some ideas to go around it. One of the ideas would be that if you fabricate millions of sources on a chip, this is the approach envisioned by PsiQuantum, then you don't know when you can operate at very low power for all the sources. Everything okay? Yeah. But you don't know which source will fire, but only one of them on average will fire, and then you just need to have a router that sends the photon at the input of your quantum computing chip. So this is one approach possible, that is possible. The other approach is to turn to what nature has given us as a single photon emitter, which is a single atom. We know since the 1980s, that when you shine a laser on a two-level system, this two-level system can only scatter one photon at a time. So that's a single photon source. Of course, it's not a good single photon source because an atom emits photons in all directions of space. So we need to make something about it. And what we could do about it is to control the way the atom emits the photon. So it's called controlling the spontaneous emission. And we can create something which we call a 1D atom. It's an atom that can only couple to one mode of the electromagnetic field, and ideally a very directive mode where I can collect the photon very efficiently. So to do that, we have the tools that fundamental physics has given us, which is cavity quantum electrodynamics. We can build a 1D atom by putting our emitter in a cavity. We are defining one mode of the electromagnetic field, and we are making sure that the atom emits more with this mode than with any other mode. We increase the interaction with that mode. And by doing that, under certain conditions, we can accelerate the spontaneous emission just in that cavity mode and not in the others. And the net result of that is that the probability for the atom to emit into the cavity mode can be given by a ratio, which is at least Fp over Fp plus 1, where Fp is the factor to which we have accelerated the spontaneous emission. So this is what we will do, what the community is doing to create efficient quantum light sources with atoms put in cavities. So it can be done with real atoms, but it's not very easy to have some compact system with that. So it's also explored with many artificial atoms, and I've made a very partial list here. But the leading technology for that now is the Semiconductor Quantum Dot that I will now explain. But you can also do that with defects in diamonds, molecules, all the type of defects in different materials. So I'm going to present now our semiconductor atom photon platform. So let's start with the Semiconductor Quantum Dot. So we start with the growth. Basically, you have this growth chamber where you have a ultra-high vacuum, and you can evaporate different key elements, gallium, aluminum, arsenide, and you send that on the substrate, and you can open and close these shutters here. So if I open one of these two, I can go gallium arsenide, but then I can close this one and open this one, and I can go aluminum arsenide. By doing that, I will have the first ingredient of my source, which is a superlattice. I can have alternative layers of aluminum arsenide, gallium arsenide, like this. You see here you see individual atoms in this image. This is TEM image. And this is a basic ingredient to fabricate an interferential mirror, a Bragg mirror. So this is the first ingredient. I built a Bragg mirror with that. I will take two of these Bragg mirrors, pile them on top of each other with a spacer in between, and this will define a Fabry-Perot cavity, a lambda cavity that confines light in the vertical direction. Then what we will do is etch this to form what we call a micropillar, which has few microns in the other direction. And when we do that, we also have confinement in the other direction, exactly like in an optical fiber. So this is my cavity. It's going to confine light in all the direction of space. And now what I want is to put the quantum dot at the center of the cavity. So now let's have a look at what is my emitter, my quantum emitter. I will use in the same growth step, I will grow now indium arsenide on gallium arsenide. And it's very different from what we were doing before, because now what happens is that these two materials don't have exactly the same lattice parameter. So when I try to grow indium arsenide on gallium arsenide, the material tries to conform to the host material, but there is a lot of strain stored here. And at some point, the system relaxes to minimize the energy, and you obtain this kind of nano lenses that actually forms a nanometric trap for emitters. So you end up, then you grow again gallium arsenide, and you end up with these 20 by 3.5 nanometer traps for carriers in the three directions of space. And these are really the quantum well in the three directions of space that we study at school, and you have discrete energy levels. So when you create one electron hole pairs or two electron hole pairs in this system, because they are trapped in a very tiny volume, they don't emit photons at the same energy. And this is how we found out in 2000, it was shown by the community that you can have single photons emitted by this kind of atom. Now it's not over. I want to put my atom at the center of the cavity. And this is, of course, a great challenge because you've understood from the way that the quantum dots are formed that we don't control their position. They have random position. So what we do is actually we have developed a technology that allows to solve this problem. We grow the mirror, with the Bragg mirrors, and then we grow the quantum dots. They have random position and random emission wavelength. And we grow a second mirror. And the idea after that is to put a photoresist. A photoresist is a polymer that we will use to draw a pattern on it. So we take that, we put that at low temperature at 4 Kelvin when we can measure the quantum dot single photon emission. And the idea is that we will measure where the quantum dots are by optical means. We excite with a laser the quantum dot emission. We find a nice quantum dot. It shows a very sharp emission line in the spectrum. And basically what we are doing is that we are scanning the sample with respect to the laser. So we are scanning here my atom, which has a nanometer time scale in a laser that has about 1 micron size. So basically, if I plot the quantum dot signal as a function of the position, I find that there is an emission that follows the laser profile. So it's about 1 micron wide, but it doesn't prevent me to know where the maximum of the curve is with a very high accuracy. And the maximum is obtained when the quantum dot is at the center of the laser, where it is the most excited. So you see that with this technique, we measure the quantum dot position. And then the idea is very simple. We have another laser, a green laser, that we will use to modify the resist properties and define a disk centered on the quantum dot. So when I find a quantum dot, I optimize very precisely its position, and then I flash with a laser and I make a hole in the resist, and this hole will be used to etch the micropillar. So with this technique, we can fabricate fields of cavity atom devices like this, where in each of the cavity, I have a quantum dot exactly at the center. And that is also at the right wavelength with respect to the cavity, because I'm doing measurements, so I know the wavelength of the quantum dot. I can select quantum dot of the wavelength I want. So with this, we fabricated high performances single photon sources. This was a turning point for our technology. So with just the devices I've just shown you here, we tested the single photon purity here. So we excite and collect the single photons. And I told you that if there is just one photon, I will never have to click on the two outputs. And the absence of peak here at 0 delay is a signature of that. So this is a high single photon purity single photon source. And then we can look at, measure the probabilities and that I do have a photon here that comes into my first objective lens here. So in 2013, we could show that we can have a single photon source with a probability of having a photon of 80%, which is still the record efficiency for a single photon source, all systems considered. But you see here, it's like 100 times more what you can get with parametric down conversion sources. Then it's very important to have indistinguishable photons to make this photon-photon gaze, like I was presenting before. And I want just to go back to this scheme that shows that there is this quantum interference. I can now write it in the formalism of Fock states. I send a 1 photon Fock state here, and I end up with these 4 possibilities, and I have a 2 here or 2 here, and in these 2 terms in the middle cancel out. What does it mean to have a 1 photon Fock state here? Well, it means that it's not the second quantization thing that you know of where you take wave planes. The states I'm considering are single photon states, single photon pulses. So it's a time-limited light pulse, which means that it's built on many frequencies. So it's actually a linear superposition of 1 photon Fock state of different frequency associated to different K vector here. And producing indistinguishable photon means that I want to produce always the same C parameters here. Whatever happens to my system, I want exactly the same superposition at the quantum level of the different frequencies to build my single photon state. And this means that if you consider fabricating a single photon source using an emitter, it means that your emitter needs to undergo what we call in quantum physics a unitary evolution, which means that the system is fully controlled before it emits a photon. And that's quite challenging if you think of it like that. There are many reasons why it shouldn't be possible with our system. if there is any kind of traps not too far from the quantum dot, I can have this kind of fluctuation of the electric field around the quantum dot, and this will lead to charge noise, which will destroy which will lead to the generation of always different photons. There is also the possibility to have coupling with phonons, and again, this could the vibration of the crystal. This would be very bad. And also, it's very important to see how I create the carriers in the quantum dot, because if I don't do it the right way, there may be some non-controlled process before spontaneous emission. So basically, we have worked since 2014 to reduce all kind of quantum noise around the quantum dot. So the first thing we have done is to reduce the charge noise. So to do that, we take the full advantage of semiconductor technology, and we actually insert the quantum dot in an NIP diode. If you do that, you can apply an electric field on the quantum dot and sweep away the charges away from the quantum dot and remove the charge noise. So to do that, we had to modify our technology. It's no longer the simple pillars that I was presenting before. We need to make an electrical contact. So to do that, we don't etch all around anymore. We make this kind of structure where we have 1D ridges and that connects the cavity to a bigger frame. It doesn't change so much the optical confinement, but it allows us to apply an electric field on the device. And we still use the technique that I was presenting before. We still put the quantum dot exactly at the center of the structure, but now we can write anything we want around the quantum dot. Then we worked on reducing the coupling to phonons. Phonons manifest themselves in the emission of a single emitter with what we call the phonon sideband. So when you have a two-level system, it should emit a photon at a very precise frequency. This is what we call the zero phonon line. This is the intrinsic emission. But if your emitter is coupled to the vibration of the crystal, it can also emit a photon while emitting or absorbing a photon. So exchanging energy, vibration energy with the crystal. And this is what we call the phonon sideband. You may have heard of them. For instance, for NV centers, this kind of phonon sideband are very big. For our quantum dot, they are not so big, just 10% of the emission at 10 Kelvin, but it's still too much to get highly indistinguishable photons. So what we have done is that when you put the quantum dot in a cavity and you accelerate the spontaneous emission, what we are actually doing is that we are accelerating the emission of this line, not the rest of them. So the net result is that we end up with a much faster emission into the zero phonon line, the line that we want, and we suppress tremendously the emission in the phonon-assisted channels. And this is a very efficient way to gain in terms of purity of the state. And this is what we showed that also experimentally. So what I was showing before was calculation, and this is experiment where we actually show and we play with temperature. We warm the sample on purpose to show that actually we don't gain too much phonon-assisted emission. So we can get rid of phonons quite efficiently like that. And the last scheme to get indistinguishable was for us to implement coherent control measurements. So the idea is just that we want to bring the system in its excited state in a fully controlled way. And these are techniques that are well known in the atomic community. It's not so easy at first glance to do that in a micron-sized system because you have a lot of scattered light, etc. But we eventually could do it, and we see here nice Rabi oscillation, which are only damped by the spontaneous emission of our two-level system. So when we gathered all this, in 2016, we managed to have not only efficient source of single photon, but source which showed very high indistinguishability. As I said, to test that, we take two of these single photons, we send them on a beam splitter, and they should exit together. So we should never have two clicks here. And you see here at 0 delay that there is hardly any signal. It's at the noise level. And this was an important breakthrough that shows that we can have highly indistinguishable photons with this system. So with that, we started to work on, see if our sources could be interesting to do some applications in quantum technologies. And the first thing that is the first steps is that maybe with this technology, we can scale up optical quantum protocols. So this, I wanted to show you this nice cartoon that was drawn during a talk I gave in 2017, that shows that now that we have a single photon and it's ready to interact at the photon gate, so that it has a great future in quantum technologies. And this is what we we think that maybe we can do with our sources, and this is what we created Quandela. The summary of the improvement that we have done with this source is shown here. If I sketch a map of single photon sources with two main performances, figures of merit, the brightness on one side here in the log scale, and the quantum purity or the indistinguishability in the other axis here. The sources that have been used so far for quantum technologies are here at the bottom right corner. You are stuck here at very low brightness if you want to have high indistinguishability. The quantum dot community, and it's really, I'm presenting the result of my group, but it's really a community progress that has been acquired over time. In the years 2013-15, we were very happy to be able to have very bright sources, like I've shown you, or either very indistinguishable sources, but we were not able to do both at the same time. And since 2016, we are now on this path here. So in 2016, we reached this value where we have very high indistinguishability with efficiencies between 10 and 20%. And since last year, we are now approaching the 50% threshold. So it means that if you consider what people were using before to implement optical quantum computing and what's now available here, you have more than a factor of 10 increase in terms of efficiency. And if you want to manipulate n photon like n qubit for quantum computation, the gain is tremendous because it's 10 power to the n. So of course, actually we did that because we had colleagues when we started to have good sources, either bright or indistinguishable, that were telling us, could you make them both at the same time? It would be interesting for us. So we worked very hard. And of course, they took this possibility, this breakthrough to first do a scheme which was very popular, which is the Boson sampling. It's a scheme that has been proposed to demonstrate quantum supremacy. So on the left, I have the classical Galton board, just a piece of wood with needles here, and I send balls, and at each, always from the center, and at each time the ball meets a needle here, it's going to go right or left, and we know that the output of that is a Gaussian distribution. The Boson sampling is something similar to that at the quantum level. So there is a first difference, is that I will not send the photon at just one input, but several outputs. And then it's not a needle which will split my photon into, it's a beam splitter. But if you see here now that I send two photons here at the input of this beam splitter, we will have the quantum interference that I was mentioning at the beginning. So it means that at each intersection here, you have quantum interferences. And if you want to know what is the output distribution of this network, well, you can. It's not going to be a Gaussian, and predicting what it's going to be is very hard. So actually, what happens is that at each intersection, these two photon interference that I was presenting before, to calculate the output, you have this term here, which is actually the permanent of a matrix. It's not the determinant of a matrix, where you would have a minus here. And it's been known for 40 years that if you want to calculate the permanent of very large matrices, it's very complicated, and actually it falls in the NP complexity class. So this Boson sampling scheme was proposed with the idea that actually so at the beginning we thought it would be possible with just 10 photons, but now we know that we need something like 50 photons, but 50 photons is very little. With 50 photons in something like 200 modes, you should not be able to compute the output distribution with the most powerful supercomputer, classical supercomputer. And this is actually what was done by the Chinese group in December with 50 modes, I would say, something in between photons and continuous variable. So when we had this kind of sources, we gave one of the art source to Andrew White from the University of Brisbane in Australia, and they did a 3-photon Boson sampling measurement, and they could show an acceleration of a factor of 100. Our colleagues in China with similar devices as us did the same year 5 photons, and they could show a speed up of a million. And in December 2019, when Google was reporting on this quantum advantage, they demonstrated a Boson sampling with 20 input photons. So this is what was done. It's very impressive, and it's not over. I mean, the progress are continuing. I want to show you here the beautiful setup that they've been using. To be clear, we will not be able to do that in my lab. It's way too complicated to do this kind of measurement, and you require a tremendous degree of control of all the mirrors, the phase, and etc. So we have been working instead toward the integration of this kind of processes, and we are doing that with two colleagues from Italy, Roberto Zelami and Fabio Schiarino, who developed optical quantum computation on chip. And they've done that for many years with frequency conversion based sources, and we are now working together to interface our quantum dot sources with their chip. So we did the first proof of principle of this kind of measurement, not with a large number of photons to start with, just with 3 photons to learn how to do that. And we did a 3-photon interference on chip here, starting with our sources. We have the photons which are emitted in time at different times moment. And we have something which we call an active demultiplexer that distributes the photons that are generated in time in different paths to enter the chip where the information is encoded in path and do the computation. This was the first step. The next generation of measurement, we will increase the number of photons. Is starting now, actually. We also worked on the scalability of our technology because we want to be able to fabricate many of these devices with reproducible performances. So here I should say that I show you here a result where we have actually studied 15 sources, and we could show that we have actually quite reproducible indistinguishability above 90% and a brightness which still fluctuates quite a lot between 7 and 20%, which is still 10 times more than what you can get with frequency conversion, but we would like to have something more reliable. And I should mention that this is still the state of the art, and we have not done better because we had to move from one building to another, and so we shut down the clean room for 2 years. So we have done no technological development for 2 years, and we are now starting again. We learned a lot from this benchmarking, and we are working to do better now. And we are now working in this direction of making the source more and more efficient. And so last year, we found a way to gain a factor of 2, although we couldn't change the devices we have because the clean room was still not working. We find new excitation schemes using actually phonon as a resources, and we gained more than a factor of 2 in the brightness, still very, very high quantum purity here. Okay, so now I want to, in this last part, yes, I want to discuss the other thing that we need to deal with when you want to develop optical quantum technologies is this photon-photon gate problem. How do we solve this photon-photon gate problem? So to be more specific, what is the problem? The problem is that I want to make a photon-photon gate, and I want to have a black box basically, and I have one control qubit, one target qubit, and at the output of my gate, I should have the qubit of the control qubit controlling the state of the target qubit. And I'm discussing photons here, right? Photons don't interact with each other. So to do that, what has been proposed back in 2001, I think, by Neil Laflamme and Milburn, is to take this quantum interference that I've discussed many times already and add detectors. If I do that, if I pile up this quantum interference wave plates and polarization and detectors, I can fabricate gates which are working very well, but not all the time, which we call them probabilistic gates. And basically, for very fundamental reason, which is actually kind of illustrated here, that the photon exit together by either one of the output ports, the success rate of the gate will never be more than 50%. So if we want to play with 20, 50 photons, it's still okay to do with that, to play with that. So in the NISQ era, we can still have fun with this method. But if we want to go to large-scale optical quantum computing, we need to solve the problem. So many ways to solve this problem that are explored by the community. The first one would be to develop single photon non-linearities. So the idea is that if I had a beam splitter which would be non-linear, I would have no problem anymore. So if I have a beam splitter that always reflects one photon, but when I send 2 photons, one is reflected, one is transmitted, I'm good. And it happens that the system I have developed to develop single photon sources is actually a system that is non-linear at the single photon level. A two-level system can only absorb one photon at a time. So if I take my 1D atom that I was presenting before, I send a 2-photon state, I can have a situation where 1 photon is emitted and the other is transmitted. And here, if I send only one will be reflected. So this is basically what we are investigating with our system. I take the same device, but now I send the laser. I am looking at and measuring what is the total field that is reflected. So what is shown here is that the reflectivity of this device. I'm scanning the laser and I see the dip of the cavity. So right now, there is no quantum dot in it, no atom. But I have this knob, which is electric field, and I can bring the quantum dot in resonance with the cavity. And when I do that, I don't have just this dip anymore. I now have a dip and a huge peak here. And this peak here is the atom reflecting the photon. So you see here, I've brought my quantum dot here in the cavity, and now it reflects light. And you see here, I have more than 95% reflection just by one atom. So we could think of this as a single atom mirror. What shows that it's a single atom mirror is that when I increase the power, well, very, very little power, on the order of picowatts, I saturate the transition. This peak disappears and I end up with as if the cavity was empty. When I saturate the transition, it's as if there is no quantum dot in it anymore. So we can show that it's actually a device with a single photon non-linearity by now sending light pulses. I want to send light pulses because in a pulse, I can tell how many photons I have on average. And I can now plot the reflectivity of the light as a function of the average photon number. And you see here that we go from a reflectivity above 65%. So it's no longer 90% as just before. And the reason is clear. It was a peak reflectivity. Now I'm sending a pulse. It has a width. So I'm integrating the pulse area over the reflectivity curve here. So it's still very high, around 65%. And when I increase the number of photons in my pulse, it saturates, the quantum dot transition saturates, and I end up with a low reflectivity. And what is remarkable on this curve, I'm sorry, I forgot to put the reference here. This was published in 2017 in Nature Nanotechnology. You see that the threshold occurs below 1 photon on average. So we have less than 1 photon on average sent on our device, and suddenly it behaves like a non-linear system. And if you look at the statistics of the light that is reflected, when you saturate the transition, there is no longer the quantum dot effect. So you end up with a G2 of 1. So just for specialists, it's what characterizes a laser light, a coherent state of light. And when we are at low power, where the quantum dot reflects most of the light, you see that the G2 is below, it's around 0.3. And that shows that actually our system is reflecting single photons. So we have a device that actually reflects single photons only, and the other photons are actually sent through or scattered in other directions. So that's one way to solve the photon-photon gate problem. The second scheme is to create cluster states of light. So this light state I was mentioning before, where you have multiple photons that are entangled together. That's a very, very important resource for the scalability of quantum computing. It was actually introduced in 2003 and studied in more detail in terms of practicality in 2017. And actually, if you have lights of states with few entangled photons, like cluster states with 3, 4, 5 photons, we can go beyond the problem of the photon-photon gate, which are not acting as we want them all the time. And we can now replace 2 photon gates by single photon gates. So it's been done with parametric down-conversion sources. So there is, it was created with up to 12 photons with this source of frequency conversion. You see the laser, you have 2 photons here, 2 photons here, etc. And then you have linear gates, and you create these large states of light. Again, this is not really scalable because each of these gates here is probabilistic. It doesn't behave as you want it all the time. There is a scalable approach that we are exploring right now, which is actually based on a spin photon gate. I will not enter into the details, but basically the idea is that if now I have a spin in my quantum dot, the optical selection rules tells me that if I excite properly the system by controlling the spin, each time a photon is emitted, it's going to be entangled with the spin in my quantum dot. So on paper, this was a theory, and there was a first proof of principle measurement done in 2016 in Israel. We can create light photons that are entangled together in as efficiently as we have done before with single photons, but now with photons that would be entangled. So we are working on that, and I think we should have progress soon. In between, we've done something which I think is very elegant and can be used in the meantime with Agay-Heisenberg, where we replace the spin of the quantum dot by a probabilistic gate. So we take our single photons, they emit photons one after the other. Then we send them on a gate where we have here just a fiber that creates a delay line. It's like an optical memory. And when the photons have a probability of going in or continue, they will meet the next photon at the beam splitter and they get entangled here. So Agay has shown theoretically and done the first demonstration with parametric non-conversion sources that you can create linear clustered state like that. So we did that with our system last year. We took our sources. They brought a setup which fitted only in a rack size, and they came with their suitcase. And it's very simple. You have just beam splitter, polarization controller, fiber, detectors, and we could demonstrate the creation of up to 4 photons entangled like that. It was very first demonstration, and we have you see the states here. These are linear cluster states encoded in polarization, and they derived a witness entanglement. And you see here that there is entanglement with confidence with up to 2 standard deviation. And the next run for us is to increase this photon number as well. And also there are some ideas to go beyond 1D cluster states with additional ideas in the scheme. Okay, I have one last thing that I want to mention before I finish, is the idea that I wanted to let you know that although it seems that all the talk I've told you is oriented towards application in quantum technologies, actually the activity of this group started with just fundamental studies of light matter interaction in semiconductors. And it turns out that all the progress that we have made to make nice single photon sources has allowed us to revisit textbook atomic physics. And we are continuing to do that. And it's actually a lot of fun. So I just want to tell you one result that we published 2 years ago, well, yes, 2 years ago, where we explored the transfer of coherence between the atom and light during spontaneous emission. When you do a coherent control of a 2-level system, you basically, it's a textbook's quantum physics, you create a superposition of ground and excited state in a 2-level system. This is what quantum mechanics tells you. But then the atoms emit photons. Does this quantum coherence at the quantum level, at the atomic level, be transferred in the photonic state? Can we create a superposition of 0 and 1 photon with a pure quantum superposition in the light field through spontaneous emission? So actually, we demonstrated that it is indeed the case, and I think it's something that was never done before with real atoms, and that we could do because our atom is getting very, very good. And also bright, so the measurements are easy to do. So just a glimpse on how we demonstrated that. It's just revisiting this quantum interference that I was mentioning before. Before I was sending light state where there was only the photon state 1. But now if I consider a pure superposition of 0 and 1, you see with different coefficients, so there is a population of vacuum, population of 1 photon and a phase. Then I calculate the state at the output of the beam splitter. And I have what I showed before, this 2, 0, minus 0, 2 state. Okay, this is what we call the Hango-Mendel interference. But now that I have a more complex state, I have other terms. I have single photon terms here. And these terms here actually depend in intensity in the relative phase between the 2 input wave packets. So actually what we could, we observed it by chance, and we had to think a lot to understand what was going on. What we could see is that now, just looking not at the coincidences, but just the single counts on the detectors, we were observing oscillations as a function of the phase at the input. And these oscillations, we could show that actually they reflect the fact that there is vacuum in the state in the coherent superposition with 1 photon, and we can extract the purity in the photon number basis of the state. So we observe this phase-dependent oscillation, and we could show actually, so I will skip that, and we could show that we actually create quantum superposition of 0 and 1 photons with a quantum purity in the photon number basis, which is very high, close to 1 as well. So this is a lot of fun. I could tell you that the next step is that we are now playing with exciting the atom several times, using atom-photon entanglement to create more complex states of light. And we are working on the paper where we show that we generate entanglement with this scheme. But also this encoding of 0 and 1 photon, actually, so we just discovered it by chance. But then I turned to my colleagues, theoretician colleagues working on boson sampling, and asked them, do you think that it could be useful for quantum computation? And they came up with a new scheme, which they call superposition boson sampling, which could be interesting also to see if it can push further the complexity of the computation that we can do. So that's one thing that we are now exploring. And also, we are also using this scheme to explore quantum thermodynamics. So we are starting to be interested in the energy cost of optical quantum computation, well, basically at a very fundamental level. And we have this work in collaboration with Alexia Ofer, where we use this actually superposition of light to explore the exchange of energy at the quantum level. And with that, I'm finished. I want to thank all the wonderful teams that I have the chance to work with. Long-term collaboration on the material development side with Aristide Lemaitre, Isabelle Sain, on the theory side with Alexia Ofer, and my close collaborators within the group, Loïc Lanco and Olivier Krebs, who are more specialists in spin physics, which is a critical expertise now that we are entering the field of building spin-photon interfaces, and all the young talented students and PhD and postdoc, Hélène Olivier, Sarah Thomas, Thierry Wancro, Marie Billard, Clément Millet, Ilse Mayette de Buiveniger, Elam Mehdi, Nathan Kos, Matthias Pons, Stephen Vine, coming from the group of Christophe Simons, who is supporting us on the theory side, and the activity led by Daniel Kimura, who joined the group a few years ago as a permanent researcher, who is trying to now transfer some of the concepts that we have developed in optics in acoustics, with Martin Esman, Omar Otis, Anne Rodriguez, and Priya. And here you see the faces of the two former PhD and postdoc students of my group who created Quandela, who is now commercializing these single photon sources. The companies, I think now there are like 16 or 20 employees, depending on when we count, and still growing. Thank you for your attention.
Thank you, Pascale. It was a wonderful talk. Really interesting and inspiring, I'm sure, for all the students and the people working in this area and related areas here in Portugal and abroad. So we have a couple questions, if you're available. Okay.
Sure.
So Haman Shudari, he's actually a Quantum Portugal Initiative grant holder. Okay. He's asking a simple question. Can you please explain how the average photon number can be less than 1?
Yes. We have a slide for that. No. It can be less than 1 so for instance, so this is exactly what quantum physics teach us, that when you have a laser, actually, you don't have a well-defined number of photons. You have a probability of having 1 photon, probability of having 2, probability of having 3, etc. And in that state specifically, there is no correlation between these different probabilities. So you have what we call I'm losing the word now. Not Boltzmann. It's not Boltzmann. Please help me, Ernesto. No.
What is it, sorry?
The statistics of the laser. So basically, you have a probability of having 1, 2, 3 photons, etc.
Poisson, is it?
Poisson statistics.
Yeah.
The Poisson statistics of having either of these photons. So you can plot the probability distribution of having n photon, and it's going to be a Lorentzian with a given mean average photon number and some distribution. Which means that when I say that I have on average half a photon, it means that sometimes I have 0, sometimes I have 1, sometimes I have 2. And you can neglect that the probability of having 3, 4, etc. But this is a superposition of these different possibilities that constitute my state of light.
Thanks a lot. We have a few other questions. Let me see. Martin Lopez, he's a researcher at INL. He's thanking you. He thinks that the work is really nice, and I agree. And he's curious about how important it is to control polarization in the cavities where the quantum dot is, especially for entangled photon generation.
Yes. So, well, I could answer differently. So it could, so for single photons, people generally prefers polarized single photons. So actually, we would like to, one of the possibility is to actually have a highly polarized cavity. If your emitter has no polarization selection rules, you can couple it to a polarized cavity and force it to emit polarized single photons. So this was done. What we do is slightly different. We actually work with cavities which have almost no birefringence, so they are mostly circular, and we actually use the linear selection rules of some of our states, and there are different states in the quantum dot, and we take states that emit linearly polarized light. But you're right, for untangled photons, if you think of polarization entanglement, you would like to have a cavity that is not spoiling the polarization properties of your source, and we need highly circular or maybe just very little splitted cavity is enough actually to create entangled photon states. So actually in 2010, we demonstrated a very bright source of entangled photons using two pillar cavities. They were next to each other, and you think that you would break the polarization symmetry, but you don't break it that much, and we got a very nice source of entangled photons like that.
Thanks. We have another question here by an anonymous attendee. He or she is thanking for a great talk, and they're asking, are all your results were done with gallium arsenide and indium arsenide quantum dots, right? And if so, they're asking if you think there's a chance that other material platforms could outperform these two materials.
Okay, so there is always a possibility to have something better in another material, that's for sure. And I am the very first to think that, because we didn't bet on these quantum dots like 5 years ago. So you never know what's going to happen when you work with new materials or materials and you understand better the physics of it. So we are playing with indium arsenide, gallium arsenide quantum dots, which emits around, you can go from 870 nanometer to 970 nanometer. So this is a spectral range that we can cover, which is not very satisfying. We would like to have other wavelengths. So if you want to go to shorter wavelengths, there are for sure gallium arsenide quantum dots in aluminum arsenide that have emerged in the last few years as excellent candidates. They don't show better properties, but they are at the same level as our quantum dots. And they operate in the 700 to 800 nanometer range. So in the middle of that, there is 780, which people from atomic physics love. And so we are also working to transfer this technology at this wavelength. We would like to go to telecom wavelengths, and for that you need to go to other materials. So you need to increase the content of indium or to go to indium phosphide. It's been a long quest, to be honest. This is more difficult. In my lab, we had this activity 10 years ago and it was stopped, and we are restarting it now because material science has improved them. Then if you're asking the question about other semiconductors, other things that are not semiconductors, I would say that from what I've learned over the last 20 years is that the emitter you're considering, that are considered, should be, I mean, the enemy of decoherence, I think in the solid state, is surfaces. I think it's a general rule. If the emitter is very close to a surface, it's going to be very hard to have very high quantum purity, I mean indistinguishability. So there are many systems that are explored right now, 2D materials, carbon nanotubes, etc. They are shown to emit nice single photons. But indistinguishability, I think it's going to be more tricky, but there are always possibility to control the surface bounds and stuff like that to get there. So I think, yes, it's just one system. There will be others.
Very nice. So it's especially nice that you mentioned that like 5 years ago, you wouldn't be betting on the best solutions you have so far, right now.
Yeah, in 2014, we were, I remember very well, different colleagues in the community, we were thinking, should we give up or not? And do something different, and just a few months later, bang, we had this indistinguishability of one and nothing was the same. So
Mm-hmm. Very nice.
It's good to know.
If I may ask a couple of questions as well. You show these pulses, okay, with controlling the photon number, hitting the quantum dot, right?
Yeah.
But if you're doing photon gates, it would be nice not to have a photon, a laser pulse, right, with this Poissonian distribution, but to have actually one of these very nice single photon states that you can prepare. So what are the difficulties associated with that?
The difficulties are very basic. It's not losing the photons on the optical table between the two. I mean, we are doing two sources experiment where we take one photon from one source and we make it interfere with a photon on the other. So we could completely similarly take one photon of the source and send it on the other. There are very, very practical problems in that in terms of just, I mean, when you have a beam splitter, you lose half of the photons, and if you want to access up and down, etc., each time you lose 50%. So if you make the math, you do the math, at the end you're thinking that you won't have so many photons coming. So it's not easy. Yeah.
So it would be something like a very long experiment, right? Until you get.
Yeah, and we are not sure what to measure actually, because if you send just single photons, what do we correlate with what? What do we measure? And it's a question we have asked our theoretician friends, and not so clear.
Okay, there's work to be done. Another question I wanted to ask, you mentioned the temperature dependence of the phonon sidebands and of the source of noise, right? At the same time, for photonic quantum computation, using room temperature equipment is an interesting proposition, right? With respect to other applications. So do we envisage using low temperature sources or room temperature sources, and how important is the temperature for the effects you're looking at?
Yeah, so my answer will be very clear. I don't believe there will be an optical quantum technology fully at room temperature. I don't believe it. The source, even if there are SPDC sources based on frequency conversion, because of the intrinsic limitation, if you pile up millions of sources to get one that fires and root it, etc., you need to detect the photon to herald, and this requires very, very efficient detectors. So, and these detectors, they work at 2 Kelvin. So you can take a supposedly room temperature source, but you need a detector at cryogenic temperature to have it work. So I think it's as well to have the source itself being cryogenic. Still, I think you still, if we think of energy and also the modularity of optical quantum computing, we are now entering a phase where we are making this kind of rack size source and detectors. You would have a rack size which would be at 2 Kelvin. You would have in it many photon source, many detectors. You have fibers coming out, and then outside you can have a room temperature computation. You can change the chip, you can change the control, etc. A lot can be done at room temperature, but I think the source and detectors will be at low temperature because, I think there are also good intrinsic reasons for that. You will never have a good quantum purity at room temperature with a solid state emitter, for instance. Okay,
but I agree with you that it's quite different to have a small quantum source or a small quantum detector, in comparison with having the whole thing inside a huge fridge, right? Yeah. So it's much more manageable, right? So
it seems actually so. All the more that in the idea of the integrated quantum computer where everything would be on chip, if you just make the math of the footprint of a gate, and if you calculate how many gates and the router, etc., it doesn't fit on a small surface. You need a huge surface. So because semiconductor technology has some size limitation, you would end up having many big chips of semiconductors that needs to be interconnected by fibers anyway. Mm-hmm. So you may as well keep all that at room temperature and have just the source and the detectors out.
Yes. Okay. Thanks. If I may ask another question, that was one you left open. Okay. So you said maybe I can talk later about Quandela, right?
Yes.
The startup company. So can you comment a bit on the differences that you've experienced? I don't know if maybe it's too long an answer, right? But between working in academia and setting up your own company, and how the this ecosystem of quantum startups is looking like, you know, from your experience inside it?
Yeah. So okay, it's a vast question.
I know.
Okay, so we decided to create Quandela. So we had the result at the end of 2015. So actually, Nicolo, the CTO and president of Quandela, was a postdoc in my group and came to me and he said, I keep having requests for having sources. We should make a company. I was like, you're crazy. And but Nicolo is very, you know what he wants, etc. So we went to the way we started the adventure, because it seems like a niche market, right? It's just simple photon sources. And so we went to see a good friend of mine, Khaled Karay, who was a physicist in quantum dot physics and created a company that you may know, which is called Atocube in Germany. That is a scientific company that creates nanopositioners, optical microscope, cryostat, etc. for actually that we are all using to develop quantum technology. So I discussed with him and tested how crazy was the idea. And actually, so he made me speak a lot and discuss all the landscape, etc. And he said that it's actually a good timing to think of that. That actually, it's a right moment maybe to consider selling single photon sources, because quantum technologies are getting some momentum, etc. So we entered the phase where in France, we have a lot of support. So we had to apply to many contests, to have fundings, to do the first step of to make what was a lab object into something which looked more like still a prototype, not a product, etc., etc. So we call that pre-maturation in France. I don't know if there is an equivalent. And so we were very well supported for 2 years by the CNRS and the different system, the university as well. And then we could create Quandela in 2017 because we had someone waiting for a source. He had an order for us. So we said, okay, let's create. And we sold our first source in 2017. And then we increased progressively the number of employees, and then we won some national contests. We got more money, more funding, blah, blah, blah. So then the story goes on like this, and we were always accompanied, we were always mentored first by Khaled Karay, but also by many other entrepreneurs. And I think this is the key. You have people guiding you, because the first thing you think of are not the important one, and the one that you think are not important are actually very important, etc., etc. So personally, I attended with my co-founders, Valerian Gies and Nicolas Somaski. We attended this business class in France, in the top of the business graduate school in France for 8 months. We had 3 days a month, full-time entrepreneurship. I had to reset my mind and understand how these people think. And it was actually at the beginning very weird, and then it became very fun, because actually it's just another logic, interesting people, interesting field. And then I should stress, and Valerian and Nicolo want me to tell you that what we discovered is that the technology is one thing. So we were very confident that our technology was important, but the team of the founders was a very important thing. So we had been working together for 4 years, and we knew each other very well. We know what we are doing well, what we are not doing so well, where we are nice, where we are pleasant, and we are able to fight and agree afterwards and all that. And the quality of the team is super important. And actually, I think what convinced a lot of people around us was not so much the technology, but the fact that we are very complementary, and we have very complementary skill and personalities that makes the story seems reliable. Okay, and then now we are in a situation where Quandela is bigger than my group. So for a few years, they were hosted by my lab. They had no equipment. They were renting everything, because the French system also allows that, which is actually very nice, because they could benefit. They were renting my cryostat, renting the clean room machine, etc. And now it's a bit of the other way around. Now that they have grown, whenever I miss some stuff, I can pick up in their lab. So there is a close collaboration, which is formalized. We have this all intellectual property rules and all this. We are very careful about legal rules, etc. But it's a very nice collaboration where we split now the different challenges between fundamental, where they sit in my team and ready to be transferred, and when they go to Quandela, and we are trying to push the full field together. So first, they are now selling sources. They have a nice list of orders now coming. They have delivered 2 or 3 systems, and there are much more coming this year. And it seems that the momentum is start to coming. And we are trying to push the community while developing also a lot of stuff on our side. So it's a very nice situation. And
okay.
That's my long answer.
No, that's great. Thanks a lot. Maybe we can just finish. We don't want to push too much, okay, in your time. Thanks a lot for agreeing to be the first speaker in the series. There's one question from the audience. Could you explain a little bit more about reducing charge noise using electrical field in the quantum dot? Is there any other tools to reduce the charge noise that you can use?
Yeah, so what we learned is that if you take a sample that is not so great and you apply an electric field, suddenly it becomes nice. So you try to understand how it works, and it seems that there are different ways of doing that to understand that. The first thing is that, so I say that we introduce a dot in a diode structure, and when in the semiconductor physics you introduce a diode, it means that you are defining the Fermi levels very well with your doping. And if you don't have doping, your Fermi level is just random, depending on the noise that you have, the residual doping that you have in your machine. So that's, I would say that, I think, in my opinion, there are 2 effects here. First, that we are canceling the non-control doping by controlling the doping. And then we are applying an electric field that actually sweeps away the charges away from the dot. That's first lesson learned. And the other is there are materials that are more prone to trap defects, like aluminium in semiconductor is very bad. So if you bring aluminium too close, not a great idea, stuff like that. So it's also a lot of experience over the year to understand what materials create charge traps, others don't, and to then engineer your system like that. I should say a third thing is that the third enemy is surfaces. When you etch, depending on the quality of the etching, you will have dangling bounds at the surface, and that's terrible for charge noise as well. So the third thing that you need to work very hard on, whatever the system, is the passivation, and passivation at the electrical level of the surfaces. And I think these kind of rules here, surface, traps, and electric field, and doping, controlling the level of doping, is something that can be applied to different systems, different recipes, probably.
Okay, thanks a lot. And I think we can wrap up here. Thanks again for being our first speaker in the series. It's a great start to the series. It's wonderful. And please, everybody who is watching, is interested in this series, stay tuned for the new announcements. We plan to have these talks every 2 weeks, and everybody is welcome to join. Thank you again, Pascale.
Thank you. See you, Ernesto. Bye.
Okay, bye-bye.